in the bottom problem so hard? One reason is a very smart 5-year-old could tell you the algorithm for that top problem, look at all possible moves to the end of the game, and choose the one that makes you win. So it's a very simple algorithm. Now, of course, there are a lot of moves, but with fast computers and some approximations, we come close to the optimal solution. When it comes to being dexterous, it's not even clear what the algorithm is you have to solve to be dexterous. And we'll see you have to both perceive and act on the world, which has a lot of problems. But let me show you cutting-edge robotics. Now, a lot of robotics is very impressive, but manipulation robotics is really still in the dark ages. So this is the end of a PhD project from one of the best robotic institutes, and the student has trained this robot to pour this water into a glass. It's a hard problem because the water sloshes about, but it can do it. But it doesn't do it with anything like the agility of a human. Now, if you want this robot to do a different task, that's another 3-year PhD program. There is no generalization at all from one task to another in robotics. Now, we can compare this to cutting-edge human performance. So what I'm going to show is Emily Fox winning the world record for cup stacking. Now, the Americans in the audience will know all about cup stacking. It's a high school sport where you have 12 cups you have to stack and unstack against the clock in a prescribed order. And this is her getting the world record in real time. And she's pretty happy. We have no idea what is going on inside her brain when she does that, and that's what we'd like to know. So in my group, what we try to do is reverse engineer how humans control movement. And it sounds like an easy problem. You send a command down, it causes muscles to contract, your arm or body moves, and you get sensory feedback from vision, from the skin, from muscles, and so on. The trouble is these signals are not the beautiful signals you want them to be. So one thing that makes controlling movement difficult is, for example, sensory feedback is extremely noisy. Now, by noise, I do not mean sound. We use it in the engineering or neuroscience sense, meaning a random noise corrupting a signal. So in the old days before digital radio, when you were tuning in your radio and you heard on the station you wanted to hear, that was the noise. But more generally, this noise is something which corrupts the signal. So for example, if you put your hand under a table and try to localize it with your other hand, you can be off by several centimeters due to the noise in sensory feedback. Similarly, when you put motor output or movement output, it's extremely noisy. Forget about trying to hit the bullseye in darts. Just aim for the same spot over and over again. You have a huge spread due to movement variability. And more than that, the outside world or task is both ambiguous and variable. The teapot could be full, it could be empty, it changes over time. So we work in a whole sensory movement task soup of noise. Now, this noise is so great that society places a huge premium on those of us who can reduce the consequences of noise. So if you're lucky enough to be able to knock a small white ball into a hole several hundred yards away using a long metal stick, our society will be willing to reward you with hundreds of millions of dollars. Now, what I want to convince you is the brain also goes to a lot of effort to reduce the negative consequences of this sort of noise and variability. And to do that, I'm going to tell you about a framework